Hello. In this video, I'll show you how to configure basic parameters and create PLC logic to control axes on CNC machine. It is a part of series of technical videos showing functionality of MTX controller, and all those videos are available on YouTube under Electric Drives and Controls, CNC Controller MTX. This presentation is a continuation of video CNC MTX channel setup. So again, we'll use latest version of IndraWorks Engineering software and open our project from previous video called MTX Initial PLC Channel 1. We'll keep this project untouched and then create and work with a copy MTX Initial PLC Channel 1 axis. First, we must configure our axis parameters and inform our control of what type of axis it will be running. So we switch on line, then NC configuration. System opens for us a window with parameters for basic machine setup. In previous video, I activated a default configuration with 1 channel and 4 axes. So I'll continue with the same setup and this time focus on axis parameters. When we click on Drive, additional configuration parameters show up. First is axis name. In default setup, this axis is called X, and we'll leave it that way. There is a nice function built in where system automatically shows us same parameters for all drives. It is called parameter instances, and we can see here right away that axis 2 has a name Y and axis 3 has a name Z. We will leave all other parameters in this group unchanged except parameter activate virtual mode. This parameter allows us to run drive as virtual and test the system without actual mechanical motion. Every drive can be configured as servo axis, spindle, or combination spindle axis. Our first drive is configured as servo axis and has dedicated for it subgroup of parameters, ax functions. We can open it and first configure our axis to be linear or rotary. Next is channel assignment. When we look into manual, we can see that there are 2 types of axes, synchronous and asynchronous. Synchronous axis, also called machining axis, must be assigned to a channel, and only those axes can interpolate. Asynchronous axes, also called auxiliary axes, are not assigned and can be called from any channel. So in our exercise, we'll make all axes synchronous and assign to channel 1. When we open Sercos tab, we can select what type of drive runs this axis with what Sercos address. Drive 2 is also a linear servo axis assigned to channel 1 with Sercos address 2, and similar with drive 3. Drive 4 is configured as combination axis spindle. So additionally to tab X function, we have here a tab spindle function. And here, system automatically assigns to this drive next available spindle index. Sercos configuration is the same like for servo axis. To add new drive to our project, we click on Main, then New, And here we can select what function this drive will have. Servo axis function, spindle function, or combination. So let's select spindle function. After a couple seconds, drive 5 shows up, and it is a spindle with spindle index 2. We can always change the drive type by right-clicking on drive and then modify info. Now we can select new function, for example axis function, and see drive 5 configured as servo axis. To remove drive from configuration, we click on main again, then delete, and then we can select last drive, in our case drive 5. That was initial basic system setup. Next step is detailed configuration of all those axes. So we click on basic parameters and then axes. Here we can see our 4 axes again, and when we click on one, a lot of additional parameters shows up. Most of them are used for special functions, so for now they can be left at default values, and we'll focus on parameters important for initial configuration. First, travel limit monitoring. There are 2 sets of over travel limits available for any axis. When we click on the first one, additional 3 parameters show up. Activation of limits with positive and negative limit values. Please note that when editing parameters, we can always click on Information button, and system will open for us a page from help file describing this parameter. Back to our parameter editor. Since our axes are in virtual mode, there is no risk of collision, so we'll leave these travel limits active just for test with limit values plus minus 1000 millimeters. And for now, we'll do the same with second travel limit. The selection of active limits is done in a PLC via dedicated signals. Next is axis velocity. Again, since it is virtual axis, I'll change it to 15 meters per minute for test purposes. For real system, we must be sure that this value will not exceed actual maximum speed for this axis. Next parameter is feed calculation, and we'll leave it in default configuration. Next very important parameter is axis acceleration. Again, for virtual axis, we can keep default values, and the same for jerk parameters. Next important parameter is axis jogging. Here we have 2 parts. First part is general jog setting with scaling, variable jog distance, acceleration and jerk. And second part is velocity selection for different jog modes. You can find detailed information about those jog modes in help file. And again, for our virtual axis, we'll leave those parameters at default values. Those are most important parameters for axis configuration. Next, we must edit parameters in all remaining axes. To make it faster, we can copy parameters from one axis, for example axis 1, and paste them to another, for example axis 2. Now we can see in axis 2 our velocity limit set to 15,000, same like in axis 1. Please note that every parameter, after we modify it, changes color to red. Also on our Project Explorer, new yellow icon with exclamation mark shows up, this is a warning from the system, and when we point on this icon, message shows up that modifications of configuration data were not applied to the control. So to activate those changes, we must restart our control. Our system will do it for us automatically when we close NC configuration window. Back in our project after restart, in the first step, same like with the logic for channels, we need to prepare internal signals to interface our PLC with NC. So we click on Access Interfaces, then Add, then Device, and then Axis Interface. System adds for us an interface for Axis 1. We can click on it and then click on Axis Interface Objects. Here we can see the system created for us two variables. First variable is Axis Interface 01 in type MTIX type, and second variable is Axis Interface 01 out type MTQX type. We can find definitions for those two types in Library Manager, then in Standard Library MT Base, and then in Data Types for NC PLC interface. So first is MT underscore IX underscore type. And this is a structure with all signals coming from NC side of our control into PLC. Second variable is MT underscore QX underscore type. And this is a structure with all signals and commands going from PLC to NC. We can find detailed description of all those signals in help file under System MTX, MTX PLC interface. Here, under Axis-related interface signals, we can see general overview of our NC to PLC signals. Our PLC program for Axis will focus only on most basic functions, and those are power on-off sequence for every axis and manual jogging function. So for power-related signals coming from NC to PLC, we'll check drive power, drive ready, and drive active. When we look on all PLC to NC signals, here are jog plus and jog minus signals, and travel limit selection signals. To enable drive from PLC, we'll use command drive on. Here in the help file, we can see more detailed description of those signals. So when we click on command QX drive on, we can see all signals and recommended timing of power on off sequence. Similar for manual jog operation, we can see description of commands jog plus, jog minus, and manual feed bit selection to select different jog speeds and increments. Back in our axis interface configuration, since we have 3 axes, next we'll add the interface for axis 2, and we can see 2 new structures for this axis, and then we add axis 3, and here are structures for this axis. Now with our interface signals configured, we can start working on PLC logic. Since this project is a continuation of project for channel configuration, let's recall a couple of steps we did before. First, we created a program PR channel, and it is dedicated for channel-related logic using a channel interface signals and special function blocks created for channel operation. So of course, we'll create a similar program. Second part of channel project is Operation Screen Simulator. And here we're able to test our channel logic in automatic and MDI mode. Our axis jogging function will be used and tested in manual mode. So to select and jog axis, we'll use buttons on right-hand side, and to select different jog modes, we'll use buttons on left side, also called MKeys. Back in our project, and first we'll create new program dedicated for our axis logic and call it PR axis. Next we open it and start with logic to select jog mode. So let's look into help file again, and we can see that there are 10 jog modes available. And to activate any of them, we must set a combination of 4 signals. There is a function block available, and it makes this selection easier. So we click on Library Manager, and then select the library MT Base Additional. Please note that this is not a standard library automatically added to the project. We added this library to the project, and you can see how in the video CNC MTX channel setup. So we click on POUs, then Drive Axis, and then Jogging. And here we can see function block MT Axis Jog Mode. We can click on it and detailed description shows up. We can see here a list of inputs and outputs, or in graphical presentation, on the left side are inputs that must be set to activate the mode, and on the right side are outputs showing us actual active mode. So now we go back to our program PR axis, and to insert our function block, first we right-click on the side of the run and select Insert Empty Box, then click on Name of the box and button to activate Input Assistant. Here on the top function blocks we can see available libraries, and then we can find and select our function block MT Ax Jog Mode. Next we hit Enter, and function block shows up in our logic. Every function block must be declared, so we type a new name for it, for example Jog Mode X1, and then built-in auto-declare function will put this function block into declaration list. Next we'll work on signals for inputs and outputs to this function block. Those signals will be coming from left MKey panel of operation screen. And editor for this panel is located at BDP 15, then screen frame, and then M panels. We'll be using a standard panel, global manual left, jog distance. Please note that every button in this panel uses 4 variables to communicate with PLC. First variable, type Boolean, assigned to field right, will change its value to true when button is pressed. Second variable, also type Boolean, assigned to field activating, work as a lamp, and when set to value true from the logic, will change the color of the button. Third variable, assigned to field block, when set to true from the logic, will block the button. And the fourth variable, assigned to field hide, when set to true from logic, will hide the button. To make our life easier, first we'll create a structure for those buttons and then use it in our logic. So we go to our logic application, then add, and then data types. Here we'll create new structure and name it Mkey. When we click on it, editor opens up, and here we can add elements with names matching panel variables. So first we'll create vertical tab group to see both editors for mPanel and for MKey structure. So first element in our structure is variable write type Boolean. Second variable activating, also Boolean. Third Boolean variable block. And the last Boolean variable hide. Next we'll declare variables for our buttons using this new structure. So we go to editor for global variables GVL HMI, and for button jog continuous we create a variable jog_count type MKey. For button jog1 micron we create a variable jog1 type MKey. For button jog10 micron we create a variable jog10 type MKey. For button jog100 micron we create a variable jog100 type MKey. And for button jog1 mm we create a variable jog1000, also type MKey. As we learned from previous video, CNC MTX initial configuration of PLC and HMI, for our variables to be available for HMI and show up in process variable list, symbol file must be updated. And to do this, we simply compile and download our project. After download and restart, we can see our jog variables active and listed in process variable list. Next step in our MKey configuration is to assign a PLC variables to individual keys. So here in mPanel editor, we need to type the names of our variables. There is much easier way to populate those fields using actual process variable list. We can simply drag and drop a variable from process list. So first, for jog continuous, we drag an element activating to field activating. And please note how system automatically adds for us an extensions application and GVL HMI. Next, we drag element block to field block, then element hide to field hide, and then element write to field write. So our button jog continuous is ready. Next, we do the same with button jog1 and put all elements from structure jog1000 into matching fields, and then do the same with all remaining buttons. Now we can go back to our program PR axis and continue working on logic. First, we will set an input enable to our function block to be always true. And we can do it by simply deleting a contact. To activate an input set jog mode 1, we'll use a variable jog1 element write. So we just start typing a name of variable, and AutoSense function will give us a list. Then we select jog1. Then we click a dot. A list of elements for this variable shows up. And then we pick element write. Next, we'll do the same for input set jog mode 10, 100, and 1000. There are 4 continuous jog modes available, and for our exercise, we use only one jog mode continuous middle. We will not use a hand wheel, so we delete this line. Then for input initial jog mode, when we are not sure what to put there, we can point on it, and library description for this input shows up. So in our case, for initial mode to be jog mode continuous middle, we'll put here value 9. Next, as a last element on the left side of the function block, we set the entire structure of axis signals from PLC to NC. On the right side of the function block are outputs showing us actual active mode. So when output jog mode 1 is activated, it will set a variable jog1 element activating to true, and our button jog1 micron will change color. Same for output jog mode 10, and it will activate button jog10. Same for buttons jog 100 and jog 1 millimeter. And the last button is jog continuous, and it will be activated by output jog mode continuous middle. Next, we'll remove all unused inputs and outputs, and we are almost ready to test our program. Additionally, for our new program to run, we must add it to an active task. So we click on PLC task, then add call, and then pick our program from the list. Now we can compile, download, and then test it. After download and restart, we can see logic running and mode continuous middle was initially activated. Next, to verify our logic and proper operation of MKeys, we'll start IndraWorks operation simulation software again. Then first, we'll switch to manual mode, and now we can simultaneously see HMI jog buttons and PLC logic. And right away, since jog continuous mode is active, we can see jog continuous button also active. Next, we click on button jog 1 millimeter. That sets the contact jog 1000 dot right, switches control to jog 1000 mode, and our button changes color. When we click on button jog 0.1 millimeter, we can see also that it is working properly. Same with button jog 10 microns and with button 1 micron. So this part of our project works properly, and we'll go back to our program and continue to work on axis logic. First, to finish logic for jog mode selection, we need to add the same function blocks for remaining axis 2 and axis 3. So the easiest way is just right-click to the left of the rung, and then just copy and paste. Next, we modify the name of our function block to jog mode Y1, and then use auto-declare function to declare it. Also, since it is mode selection for axis 2, we need to change the interface structure this block works with to axis interface 02 out. Please note that we already wrote two outputs for button activation with function block for axis 1. So to avoid writing to the same outputs many times, we will delete those outputs here. Next, we'll do the same for axis 3 and make a function block jog mode Z1 working with axis interface 03 out. Next, we'll add the logic to select and jog our axis, and to test it, we'll add some buttons and lights to our operation screen. So we open our GVL HMI global variable list, and here add some variables to operate those buttons. First button for axis selection will be PB select X type boolean added to all other global buttons. Second will be variable PB select Y, and third will be variable PB select Z. To jog axis, we'll add variable PB jog plus and PB jog minus. All those buttons have LED lights, so to operate them, we'll add matching variables in global lights group. Next, we go back to program PR axis and add new network. To select or deselect axis for jogging, we use toggle function block. So first, we add empty box. Then, using input assistant, select from library RIL utilities flip-flops and function block IL toggle. We'll give it a name FB select X and let the system auto-declare it. State change on input execute will toggle output, so here we'll use variable PB select X, and our output will control variable LT select X. We'll not use input set, so we just delete this contact, and we use input reset to deactivate jog selection when our control is not in a manual mode. Next, we copy and paste this rung, declare function block as FB select Y. On the input execute, we change the variable to PB select Y, and the output will control variable LT select Y. Next, we copy and paste again and modify to work with Z axis. To jog the axis, we need to set axis interface signal QX jog plus or QX jog minus. So let's create new rung and insert new coil. And here, for axis X jog plus, we assign to this coil a signal axis interface 0 and out dot QX jog plus. This coil will be activated when axis X is selected, and that means signal LT select X is true, and when push button PB jog plus is pushed. For axis X to jog minus, we need to keep our axis selection, and using signal PB jog minus, activate signal axis interface 0 and out QX jog minus. Next, we'll copy this logic for axis Y, and then copy it again for axis Z. Next, we'll add the logic to indicate jogging motion. So we insert new coil and assign to it a light in push button jog plus. Then we'll use signal coming from control, axis interface 01 in dot IAX travel command. This signal indicates that command was issued and the axis is moving. To check what direction our axis is moving, we use signal IX travel direction negative. And since we want to know if axis is moving in positive direction, we will negate this signal. This indication is from only one axis. So next we'll add a parallel indication from axis 2 and then from axis 3. For lamp at push button jog minus, we use the same logic, but in this case all direction signals are not negated. So our basic logic for jogging is finished, and next we'll compile it and download. Now we'll test it using Operation Simulator. First, we'll switch to manual mode. Then we touch and hold VAM keys tab and activate edit mode for manual VAM. Next, we can copy one of the existing buttons and paste it into new place. This new button will be used to select x-axis, and we'll edit it right here. First, we'll select variables this button will work with, and we can drag and drop them from process variable list automatically updated by the system. So first, we'll drag a variable pbSelectX and drop it into variable key place. This variable will be activated when we push our button. Next, we'll drag variable LTSelectX into field variable LED. When this variable is activated in our PLC program, small LED in the button will light up. Next, we'll change the text inside the button and increase the font size to 32. We'll not use any icons in this button, and all other settings like dimensions, safety, and effect will be unchanged. So here's our X button. Next, we'll copy this button and then edit it to be our Y button. And then we'll do it again and create Z button. For our button jog plus, first we'll copy button for automatic mode, then edit it and put variables for jog plus, change text to jog plus, and change icon. And last, we'll do this again and create button jog minus. Next, we'll exit configuration, and we are ready to test it. First, we must set feed rate override to value different than 0, and then we'll watch simultaneously operation buttons and their logic. So for axis selection, when we click on X, our variable LTSelectX was set and LED in button is on. When we click again, variable and LED are off. Next, we test it for Y-axis and then for Z. Next, we'll activate all three axes, then switch mode to automatic, and we can see that our logic works properly and all axes are deselected. Now, let's jog our axis and watch the logic. So first, jog continuous is active. We select X-axis, then push button jog plus, and see our virtual axis moving. When we click on jog minus, we can see our axis moving in negative direction. Next, we deselect X-axis, select Y-axis, and then switch jog mode from continuous to jog 1 mm. Now, when we push jog plus, our axis will move 1 mm and stop. When we push jog plus again, axis will again move only 1 mm. Same as with jog minus. Every time we push it, axis moves 1 mm in negative direction. And the last test of jogging is Z-axis with 0.1 mm step. And we can see here that every time we push jog plus or jog minus, axis moves 0.1 mm in plus or minus direction. Next, we'll replace our virtual axis with the real one and add some logic to power and enable it. First, we'll add new program and name it PR Power. Before we start working on this program, let's look into help file again. Here we can see 4 interface signals available for power sequence. First signal from the drive, IX drive power, tells us that drive is communicating with our control and is enabled for power activation. When the power is connected, interface signal IX drive ready is activated. Now we can enable the drive by setting the output QX drive on, and then, after drive is enabled and ready for operation, we'll get back interface signal IX drive active. Back in our program, and now we'll add the rank for axis 1. So insert new coil, and it will be our output to enable drive QX drive on. Next, we'll add condition signals from the drive. So first contact is a signal I-axis drive power, and the second is I-axis drive ready. The last one is a local contact power on to control the output. Next, we'll make a similar rung for axis 2, and then another one for axis 3. Next, we'll add this new program to task list, and then compile and download. After restart, we can see our program running, but since all axes in our project are virtual, there are no signals coming back from the drives. So in the next step, I will replace one of the virtual axes with a real one. So I prepared one of our IndraWorks CS demo units to be this axis. This drive can be connected to power with internal contactor. It is connected to our control using Sercos protocol, and I assign to it a Sercos address 2. So next we'll go online with our control and then edit parameters again. Here we'll go to configuration data setup, then basic NC configuration, and then drive 2, activate virtual mode. We'll change this parameter to no, and then for this change to take effect, we need to restart our control. After restart, we can see right away a new element in our project, and it is our IndraWorks CS on the Sercos communication network with address 2. When we click on it, new menus show up, and here we can configure this drive. When we switch our PLC online, we can also see important change. And now, with drive 2 connected and ready to be powered, interface signal IX drive power from this axis is coming back as true. Additionally, when I activate contactor in drive demo and power is connected to the drive, a second interface signal IX drive ready also comes back as true. So now we can finish our logic for drive power and test it with axis 2. First, we'll edit our GVL HMI global variable list and add here 2 push buttons: PB power on, PB power off, and one light, LT power on. Next, in program PR power, we'll add new rank to control our supporting local variable power on, And we'll do it using our new push buttons. To control a light LT power on, we'll use axis interface signal IAX drive act coming from axis 2. Next, compile and download, and we are ready to test it. We'll do it again using operation screen. I already added 2 push buttons for power on and off, and next we'll move this panel to see a logic. We can see that IAX drive power is on. Next, I'll activate contactor and connect the power. And next, I'll push power on button. Our power on contact latches itself and activates output QX drive on. Our drive is powered and enabled, and axis interface signal IAX drive active is on. When we push power off button, enable signal for axis is removed and drive is not active. Let's do it again, but this time we'll additionally communicate to the drive via Sercos service channel and monitor axis status. We'll show it simultaneously with our logic and with all additional details. So here we can see drive status message, current values of position, velocity, acceleration and torque, active status bits, and additional messages. So initially, our drive has no errors and is ready for power on. You can see status bit ready for operation and interface signal drive power is on. When we look on front display of our drive, we can also see status BB. First, we'll activate demo contactor and connect the power. We can see a message control and power section ready for operation. Status is AB, and our interface signal drive ready is on. Next, we'll get our operation screen back and push power on button. Now we can see that motion is enabled with primary operation mode, and it is position control with encoder 1. Our status is AF drive with torque, and interface signal drive active in our logic is on. Now our real axis is powered and ready, and we can jog it. So first we set feed rate override to 100% and select mode jog continuous. Next we'll select y-axis, and then when we push jog plus and jog minus, you can see axis moving, position, velocity, acceleration and torque. As you can see, to acknowledge power on status, we used only signal from axis 2 because we knew all other axes are virtual. And in our logic, we might need to verify what is the status of the axis. So next, we'll create a function block that will show us if our axes are enabled, virtual, and running Sercos communication. We'll read machine parameters using standard function block MKey config data. This function block is located in library MKey base, then PLUs, and then NC data. When we click on it, we can see that we need to supply a channel number and machine parameter block, and depending on parameter, system will return single value or array of them. We can find those numbers of machine parameters blocks in machine parameters. So for drive enabled, we can find block numbers with attributes, and it is 1001, 00001. For activation of Sercos communication, a block number is 1050, 00002, And for activation of virtual mode, a block number is 1001 00010. Additionally, since we are in a parameter editor, let's modify some parameters for our future tests. We already have one axis in non-virtual mode, and it is axis 2. All axes by default are enabled, so we'll modify axis 4 and set enabled to no. And next we'll add axis 5, set it to be virtual, and deactivate Sercos communication. So now for our test, we have one axis that is not virtual, one axis not enabled, and one axis without active Sercos communication. For those parameters to take effect, we need to restart control, and now we are ready to create our new function block. So first, we'll add a new POU. We name it FB axis status, select it to be function block, and pick structure text to be implementation language. Next, we open editor for this block and start with general comment. Next, we'll call our function block MKey config data to read enabled axis. So we name it FB read1 and let system to auto-declare it. Using input assistant, we'll pick a type MKey config data direct from library. Once function block is declared, we can open parentheses and system will automatically show us a list of all inputs and outputs for this function block. First input is start and it is a flag for new request. And we'll control this input with local Boolean variable mread Makoda1. Second input is channel selection. So we'll set here channel 1. Next input is block number. We'll control this input with variable block number axis enabled. This variable is type unsigned double integer, and to read parameter for axis enable, we need to set its initial value to 1001000001. Next element is destination address of the data. So we'll set it as an address to dedicated variable ListAxisEnabled. System will read for us information if axis is enabled for all allowed axes. So our variable ListAxisEnabled must be an array with up to 64 elements. To make this array, we'll use array wizard built into auto-declare function. So first, we'll set dimensions. An MTX control can have up to 64 axes, but in our case, we'll watch only first 6. The type of all elements of the array is byte. Before finishing declaring this variable, please note that our list must be available for our logic outside of the function block. So we must declare it as an output. Here you can see finish declaration. And the last input to the function block is max size. And here we must declare memory for our data. And to set it, we'll use operator size of for variable ListAxisEnabled. From output to our block, we'll use only error without any variable assigned. There is no need to read this data continuously. So add the logic to make sure input start is activated only once per cycle. So use output active from function block to reset variable mread Makoda1 and prevent function block from reading data again. To activate this variable for one time, we'll use input enable and special trigger. So first we'll create new function block tr start and declare it as a type rtrig. And that means it will react on raising edge of variable enable. And this variable enable is type boolean and is set as our input. Output of this trigger will be true only for one PLC cycle, and we'll use it to set our variable mread Mkey 1. Next, we'll add the logic to make a list of virtual axes. First, we'll put new function block FB Mkey 2 type MT config data. Input start will be controlled by variable mread Mkey 2. Channel selection again, channel 1. Input block number is set by variable block number virtual axis, and this variable is initially set to value 1001 00010, and the data is stored in variable list virtual axis. For input max size, we'll again use operator size of with variable list virtual axis. Next, we'll add the logic to control a start of this block. So first we make sure that variable mread Mkey 2 is reset after one read, and we activate this variable when we finish previous block. The last element of our function block will be a logic to check Sercos communication. So here we have a third function block FB Mkey 3 type MT config data. Block number input is configured to initial value 1050000002 with variable block number Sercos active, and the result data is stored into array list Sercos active. Please note that Sercos active data is type unsigned double integer. To finish our function block, we'll add the logic to control input start using variable mread Mkey 3. So let's test it. First, we'll go to program PR General and add new round. Next, we'll add empty box and using input assistant, assign to it our function block. We name it FB axis status 1 and let the system auto-declare it. To control input enable, we'll create local contact test1 and leave all outputs empty with no variables assigned. Next, compile and download. We can see our program running. And next, we'll rearrange our windows to simultaneously see input and inside of our function block. Now we can expand all output arrays and see detailed status of all axes. Next, we'll set our test1 contact, and right away, system shows us all existing axes enabled except axis 4, all existing axes set as virtual except axis 2, and all axes with Sercos activated except axis 5. So we can see that our function block works properly. And next, we'll use information about axis virtual status in our program PR Power. So first we'll go to our global variable list GVL HMI and add here 3 global variables matching our outputs from function block. Next, we'll go back to our program PR General and assign those variables to outputs of our function block. We'll also set input enable to true and that means we'll run this block only once after PLC start. Now we can go to program PR power. And here we'll add new logic for axis 1. Now, to show if axis is powered, we have two signals. If axis is real, bit 0 of our element 1, axis 1, of our list shows false. And only indication if axis is powered is interface signal IAX drive act. If axis is virtual, our list signal is true and axis behaves as powered up. Next, we'll make the same logic for axis 2 and axis 3. Then make one rung for our light power on and verify if all axes are powered. After compile and download, we can see right away that axis 1 and 3 are virtual and already powered. Axis 2 is not virtual. So next we'll use our operation screen, push a button, and our indicator shows all axes powered. That was a last step of my presentation. Thank you for your attention.